Have you ever wondered how you can prove something is true for an infinite number of cases? I mean, you can't test every single one, right? Well, that's the magic of mathematical induction. It is one of the most powerful tools in logic, and by the end of this, you'll get exactly how it works and how it can be twisted to prove the impossible.
But first, let's start with a puzzle. Do you think a totally rigorous mathematical proof could be used to show that every single person on Earth is the exact same height? It sounds absolutely absurd, doesn't it? Well, today we're going to walk through a seemingly logical proof that claims to do just that. Let's see how it's built.
So here's the claim we're going to investigate. The statement is this: for any group of people, no matter the size, everyone in that group has to have the same height. And we're going to try and prove this using the framework of mathematical induction. Now just look at this structure. It seems perfectly logical, doesn't it? This is the classic three-part setup for an induction proof. Step 1, the base case. For a group of just one person, our statement is true. Of course it is. Step 2 is the assumption. We're just going to assume the statement is true for any group of size n. And then step 3, the inductive step, we'll try to prove that if it's true for n, it must also be true for a group of n plus 1. Okay, let's start the proof. Picture a group of n plus 1 people. We ask one person, let's call them x, to just step out for a second. Now we have a group of n people left. Now, according to our big assumption, any group of n people has the same height. So everyone in this leftover group, let's call it group B, is the same height. So far, so good? Right, now x comes back in, and a different person, y, steps out. So once again, we have a group of n people. We'll call this one group C. And just like before, our assumption tells us that everyone in group C must also be the exact same height. And here is where it all seems to click into place. The people who never left the group, the ones in the middle, they were part of both group B and group C. Since everyone in group B is the same height, and everyone in group C is the same height, well, that means person X and person Y have to be the same height as those common members. And just like that, it looks like we've proven that everyone in the n plus 1 group has the same height. The proof feels complete. So, what just happened? We've apparently just proven something impossible. Obviously, there has to be a mistake somewhere in that logic. To find the crack in this argument, we first need to build a really solid foundation of what mathematical induction actually is. Okay, let's step away from that weird paradox for a minute and build our intuition with a really simple analogy: dominoes. This is, hands down, the best way to get a feel for the core logic of induction. Imagine a line of dominoes that goes on forever. You want to be absolutely 100% certain that every single one of them is going to fall. The good news is, you don't have to watch them all topple. You just need to know two fundamental things. It really just boils down to two simple rules. First, you have to know for a fact that the first domino will fall. That's rule 1. You got to give it that initial push. Second, you have to know that the dominoes are spaced correctly, that if any given domino falls, it is guaranteed to knock over the next one. That's rule 2. If you can prove both of those things are true, you've just proven the entire infinite line will fall. Okay, so let's translate that simple domino logic into the formal language of a mathematical proof. This is where we build our real toolkit for solving this thing. These two rules have formal names. Tipping that first domino, that's called the basis step, or sometimes the base case. This is where you prove the statement is true for the very first value, which is usually n equals 1. Making sure that the chain reaction works is the inductive step. Here, you get to assume the statement is true for some domino n, and then you use that assumption to prove it has to be true for the very next domino, n plus 1. All right, let's put this into practice with a classic proof. We want to prove that the sum of the first n numbers, 1 plus 2 plus 3, and so on, is always equal to that formula on the right, n times n plus 1, all divided by 2. This is a huge result, and induction is the perfect tool to prove it's true for every single possible n. So let's follow the steps. First, the basis step, for n equals 1. Does it work? The sum is just 1? The formula gives us 1 times 1 plus 1, divided by 2, which is 1. Boom, perfect. The first domino is down. Now for the inductive step. We get to assume the formula works for n. Our whole goal is to prove it must then work for n plus 1. We start with the sum up to n plus 1, which is really just the sum up to n, with that extra n plus 1 term tacked on. And because of our assumption, we can just swap out that sum up to n part with our formula. After a little bit of algebra, everything simplifies perfectly to the formula we were aiming for. The chain reaction is real. It works. All right, we've got our domino analogy, and we've walked through a correct proof. We are now fully equipped. It's time to go back to that impossible proof about everyone being the same height and find the fatal flaw. So, where exactly does the logic break down? Well, for any group of 3 or more, the argument actually holds up. If you have 3 people, there's always an overlapping person in the middle to connect the heights of x and y. But what about that very first jump? The one from a group of 1 to a group of 2? In that case, our n+1 group has only 2 people. When you remove person x, you're just left with y. When you remove person y, you're just left with x. There is no one left in the middle. There is no overlapping group. The logical bridge that connects their heights is completely missing. And that's it. That's the fatal flaw. The logic of our inductive step, the whole mechanism that's supposed to guarantee the chain reaction, is totally invalid for that first crucial step from n=1 to n=2. The base case was fine, the first domino was tipped, but the connection to the second domino was never actually made. The entire chain reaction fails before it even gets a chance to start. Uncovering that paradox just goes to show you how careful you have to be. Induction is incredibly powerful, but every single link in that chain has to be secure. So let's look at a few common mistakes people make, and then check out an even more powerful version of this tool. Yeah, research shows that students often get tripped up in a few key ways. A big one is trying to prove the n case is true when the real goal is to prove the connection from n to n+1. Sometimes people will check the base case for n=1, n=2, and n=3, when really only that first one was needed. It can also get confusing if a proof needs to start at n=3 or if it only deals with, say, even numbers, which means your base case and your step size would have to change. But what if knocking over the next domino required the weight of all the previous dominoes combined? For some proofs, just knowing the n case is true isn't enough to make the jump. That's where a more powerful variant called complete induction comes in. Instead of just assuming the statement is true for n, you get to assume it's true for every single case that came before n+1. This lets you do some really elegant proofs, like this kind of fun one. All natural numbers are special. To prove it, we assume the opposite is true. That means there must be some set of non-special numbers. Okay, so in that set, there has to be a smallest non-special number. And to know it's the smallest, we rely on our assumption that all the numbers before it were special. But wait a minute, being the very first smallest number that isn't special, that's a pretty special property, isn't it? That's a contradiction, which means our initial assumption was wrong. All numbers must be special. So we started with a bizarre paradox and ended with a proof that every number is special. What is the big idea you should remember from all of this? Here's the key takeaway. Mathematical induction is not just some formula you have to memorize for a test. It's a profound way of thinking. It's about building an unbreakable chain of logic. You secure that very first link with your base case, and then you prove that every single link is forged perfectly to the next with your inductive step. Once you've done that, you've built a chain that can stretch all the way to infinity.